good afternoon, and thank you for sharing your lunchtime with me. I hope this turns out delicious as well. Today, I'll be talking about achieving cost competitiveness or getting to an economic tipping point when we're looking at green hydrogen for use to decarbonize industry. A lot of people contributed to this work in my group, so I'm just, taking the hits for everyone. But it's been a group effort to gather all these interventions and explore their potential. Just a bit of what I do. So in my group, GLab, we develop tools to explore how interventions can improve the economic viability of sustainable solutions required to decarbonize energy intensive sectors. So we look at sustainable solutions like CCUS, fuel switching to hydrogen, synthetic fuels. We look at electrification of industry and carbon removal with direct air capture. We're majorly focused on how interventions can improve their economic viability. And we look at their use in 6 sectors that are responsible for 31% of global carbon emissions: the refineries, chemicals, cement, petrochemicals, shipping, and aviation. But today, and some of the interventions we look at are here. Now, our goal is to get to some form of economic tipping point because of the difference in cost of a sustainable solution and the business as usual. And we explore how internal interventions and external interventions, looking at market-based policies like a carbon tax, a subsidy on fuels, a contract for difference, purchase agreements, carbon trading, can get to economic tipping points. But today, we're focusing on green hydrogen. We have other presentations focusing on different other sustainable solutions. And I'll start with a background. I'll talk about exploring interventions, present the methodology reviews in very simple terms, present a case study of the UK and conclusions. And I'm happy to take questions at the end as well, both online and in person. Now, hydrogen is important, and there's a general consensus that it's an increasing important alternative. We need molecules as well, especially for heavy sectors. So it can be used as a fuel, but also as a feedstock. And there are different colors of hydrogen. And I'm only looking at green. I'm not saying green is the best, but it is a sustainable option, and it's considered to be clean. Now, today, 65% of hydrogen is demanded in the chemicals industry to make ammonia, to make resins, and we have about 25% for refining. So industry has that experience in using hydrogen, although the hydrogen in circulation today is gray hydrogen. But transitioning these sectors will need to replace gray hydrogen with green hydrogen. Now, the potential of hydrogen is great. I mean, you could link it to the electricity system to use as storage. You could manufacture synthetic fuels from that molecules to use in shipping, aviation, and hydrogen as a fuel or a feedstock can be used in oil refinery, replacing green hydrogen, iron, and steel. So the potential is great, but the challenge is the economic challenge. Now, this is not the only challenge, but this is what I look at in my research. And we've gathered here prices of hydrogen we've seen from literature, from grey literature, academic literature, and you can see that widespread in the price of green hydrogen compared to blue hydrogen, or even compared to grey hydrogen, and even compared to biomethane and natural gas. And it is an economic challenge. To me, it looks like a mountain to climb in trying to bring down the cost of green hydrogen so it can compete with natural gas and even compete with biomethane as well as alternative fuels. When you zero in on green hydrogen from offshore wind, this is the data we collected from different sources to show the spread on the levelized cost of hydrogen from now up until 2050. I mean, we see a reducing trend, but the spread is great, but it's still higher than the price of natural gas or the price of blue hydrogen. But despite this economic challenge, hydrogen comes up in decarbonization pathways for different countries. In the United Kingdom, that's how much hydrogen is required to decarbonize industry. And that's a mix of blue and green hydrogen because the UK is taking a twin track approach to the hydrogen economy. Now, if we look at the scenarios, focus on UK industry and focus on the potential of green hydrogen, especially green hydrogen from offshore wind, we see that by 2050, we need about 70 terawatt hour, 73 also terawatt hour of green hydrogen to get to net zero within the industrial sectors. And hydrogen is not the only solution. There's still carbon capture, utilization, and storage. There's still a bit of energy efficiency, but that's the wedge for hydrogen in UK industry. So the potential is great. The potential to achieve net zero using hydrogen in the industrial sector is great, but then there is that economic challenge that we need to deal with. And this is a picture of the economic challenge, right? So that's the price of green hydrogen from dedicated offshore wind. So the pointer doesn't work on the screen, so I'll use my hand if that's okay. And that's the range of natural gas price from now to 2050. And if natural gas price is high, there's a good business case for green hydrogen. But if natural gas price is low, then it's a bad business case for green hydrogen. Like I said, there are other challenges with deploying green hydrogen. There's infrastructure, there are losses in conversion, there's thinking about the renewable energy availability, thinking about impact on the grid, thinking about the water required, the material and supply chain constraints, thinking about regulations and safety protocols. And there's also the public perception, especially regarding safety. But again, my research addresses the economic challenge, and I recognize all these other challenges that are equally as important. Now, that's why we need interventions to support reducing the cost of green hydrogen or penalizing the use of natural gas. So at some point, we get to an economic tipping point where it becomes economically viable to use green hydrogen. And there are several interventions. We divide them into two. You could have internal intervention on what you do with the technology. So what you do with electrolyzers, you can improve electrolyzer performance, what you do with the system. So electrolyzers give out waste heat. You could extract some economic value by exploiting the waste heat from electrolyzers. Electrolyzers also give up oxygen. It's possible to exploit the oxygen to generate some economic value that could reduce the price of green hydrogen. And it's possible to use curtailed wind, which will give some economic benefit. Then we also have external intervention. So this could come from public funding, especially market-based or fiscal policies and private finance. And what we did was to explore the role of these internal interventions and external interventions one by one to see how they could either bring down the price, the levelized cost of hydrogen, or increase the price of natural gas by taxing natural gas to see how it's possible to make hydrogen cost competitive. And this is just a summary of the specific internal and external interventions I'll be talking about today. So I'll look at an internal intervention from curtailed offshore wind. The UK, we're looking at 50 gigawatts of offshore wind capacity by 2030 and between 65 and 125 by 2050. Now, in 2021, we lost about 806 billion up until 2021. Sorry, we lost about 806 million pounds from curtailed offshore wind. And it's possible to use that curtailed offshore wind to make hydrogen, and we see the impact on the economy. We also look at an internal intervention from utilizing electrolyzer waste heat for district heating in the UK, looking at future projections of heating networks in the UK. I will look at an external intervention from current policy in the UK for green hydrogen. So we have a capital grant of £26 million. We have the emissions trading scheme, the UK emissions trading scheme, which is replacing the EU's emissions trading scheme, and hydrogen business models, which are supposed to pay a premium on hydrogen price related to natural gas. And something that's becoming increasingly important is the use of private finance. So we'll look at sustainability-linked bonds as an intervention to support reducing the levelized cost of hydrogen, so it's cost competitive for industry to use. I'll go over these interventions one by one. So when you're talking about electrolyzer wastage utilization, we presented on this in detail last year. It's just trying to use that if 26% of electrolyzer heat is lost, input is electrical input is lost as heat at 50 to 70 degrees C, it's possible to use that heat for district heating, and there could be some economic value of using that heat, and that could reduce the levelized cost of hydrogen. So we look at district heating networks in the UK, the future projections of district heating network to see how much heat is required and take into account the cost of building out the network, the cost of pumping the heat, so we can have a true estimate of the cost and how it impacts the levelized cost of hydrogen. The second intervention will look at, based on electrolyzer waste heat utilization. So we built an exploratory techno-economic model to see the impact on the levelized cost of hydrogen. So the dark blue bars are the levelized cost of hydrogen from dedicated offshore wind. And you see that in the best scenarios, utilizing waste heat from the electrolyzers reduces the levelized cost of hydrogen, but it's still not cost competitive with blue hydrogen or even with natural gas. But we see there's a good economic potential because the heating is at 70 degrees C, so that's a good quality heat for district heating. The second intervention we'll look at is the economic value of curtailed offshore wind. So is it possible to use curtailed offshore wind to generate green hydrogen and use it for industry? And we've seen that potential in terms of the cumulative installed capacity of offshore wind by 2050 and how much the government lost by 2021. And here is just up from 2009 to 2021, we show how much onshore wind was generated in the UK, offshore wind, and how much of that was curtailed. And this is just historical curtailment of offshore wind to show it currently happens. Now, if you look into the future, based on the projections for cumulative installed capacity for offshore wind and what is being generated, we see that curtailment continues to increase. And you're looking at about 10 gigawatts by 2050, not in total, that's just per year. Now, if we take this chunk of curtailed offshore wind and use to generate hydrogen, green hydrogen, of course, there will be other uses for curtailed offshore wind, so I'm a bit biased to green hydrogen. So we use all that to generate green hydrogen and compare it with industrial demand for green hydrogen. That's what this graph does. So this is the industrial demand for green hydrogen up until 2050 to align with our net zero objective. And then you see the hydrogen from curtailed offshore wind based on what has been curtailed, and the residual hydrogen, which will be from dedicated offshore wind. So curtailed offshore wind, hydrogen from curtailed offshore wind in the UK can meet a large proportion of hydrogen demand, and we'll still need dedicated offshore wind. So the energy balance is what I've shown there. Again, I'm biased towards using what is curtailed for hydrogen. I mean, it can be used for other things, but let's assume that hydrogen is the main one used. Now, the last intervention, or the second to the last intervention, we explored a market-based policy. So we look at what the UK government is serious about in the hydrogen economy, and we looked at the IHAP, which offers capital funding of £26 million. We looked at the UK ETS and the hydrogen business model that is being proposed in the UK. Now, the interesting thing about the UK emissions trading scheme is that it can support green hydrogen because of the market advantage it creates from increasing the cost of carbon-intensive fuels. The UK hydrogen business model just provides some financial support that pays for the difference between hydrogen, the cost gap between green hydrogen and cheaper fossil fuel alternatives like natural gas. Now, with the UK hydrogen business model, someone has to bear the bill, someone has to pick up the bill. So what we've done is to show that the UK revenues from the UK ETS can support funding the UK hydrogen business model. There's enough money there if hypothecation is allowed in the UK or some sorts, again, to just have a closed loop funding circle. The final intervention we looked at was private finance, and that's because the internal interventions were not sufficient. They could reduce the price, but we didn't see that cost competitiveness with natural gas. The policy wasn't sufficient. I'll show the results in a bit. So we thought, let's look at what's out there. So you've got these sustainability linked bonds that are performance-based financing. They currently exist for renewable electricity projects in the UK, and they are debt instruments where the returns are linked to what's happening. So we explored all the SLBs in the UK and tried to understand what the KPIs are and if majority of the KPIs are linked to greenhouse gas emissions. So there's just the evidence that majority of the sustainability linked bonds in the UK, the KPIs are linked to greenhouse emissions from renewable energy. So that gave us the confidence to explore the use of LCBs, SLBs as an intervention to support hydrogen cost reduction. SLBs are just money given per unit of renewable energy installed. We looked again at all the SLBs in the UK today. There are about 852 SLBs that are used by different organizations based on the renewable capacities. So it could be capacities to generate themselves or some form of money for power to support power purchase agreements. And this gives us an idea of the size of the SLBs depending on the renewable capacity. Now, if you look at the green hydrogen required to satisfy industrial demand, we worked out how much renewables will be required. That's the orange triangles to see if it fits within the current scope of SLBs in the UK, and it does. So it could be used as a potential intervention to make green hydrogen cost competitive. And the next step is to bring together all these interventions through a methodology that we've titled the Market Penetration Assessment of Green Hydrogen. There's a lot of data collection of hydrogen demand, different scenarios, fuel prices, different scenarios, existing policies, sustainability-linked bonds, and we estimate the demand for hydrogen, fuel emission factors, because that's related to the emission trading scheme, and worked out what the levelized cost of hydrogen is, including load factors for offshore wind, take into account how that changes with different interventions, and build scenarios around the input so we can account for uncertainties in the values. And these are just some other equations we used in the model to evaluate the impact of policies, measure the cost parity with dedicated green, gray, blue, and natural gas, and some other equations we use in the model, especially regarding the policies, because we have the hydrogen business model where we need to determine a strike price together with the capital grants and how we share the capital grants or quantify the impact of the capital grant. Now, we applied all this to a UK case study. It's easy to get the data, but also there is some serious commitment from the UK government in pushing for a hydrogen economy or hydrogen to be part of the decarbonisation pathway. So this is just a reminder of the diagram I showed before of demand for green hydrogen in industry to support UK's net zero ambition and the interventions we looked at. So using curtailed offshore wind, making sure we can get some economic value from electrolyser wastage utilization to base trade policies, as well as looking at private finance. And the goal again is to see how this combination of interventions can create some form of economic tipping point. So how can we reduce the price of the levelized cost of green hydrogen based on these interventions? Any questions so far? Yes.
One of the slides when you were talking about using the waste or curtailed offshore wind, were you saying that just using curtailed offshore wind you can get to 70 terawatt hours? Yes. So the chart, right? Just purely from curtailed.
By 2050, yes. If you use all the curtailed offshore wind predicted in the UK for hydrogen, you'll be able to meet the demand in 2050. Again, that's me being biased because there will be other users for the curtailed offshore wind. Okay, so we'll go into the results. So what I'll explain what we showed here, right? So this is the orange is the price of natural gas, and we've tried to predict the price of natural gas under different scenarios, and it's going to be between X and Y. We're somewhere around here today, the high price of natural gas. The purple shows the price of green hydrogen from dedicated offshore wind. And we predict the price from now to 2050, and that's an average price because it's from different scenarios. Now, if you utilize waste heat from the electrolyzers to satisfy or to make or for district heating, then the price reduces to the green line. So we see that reduction in the price of hydrogen from just the economic value of waste heat. And using electrolyzer waste heat for district heating can reduce the levelized cost of hydrogen by about 16% on average. If you now consider the policies in the UK, so a mix of the IHAP, the UK ETS, based on the low price today and looking at future increases in the carbon price under the ETS, we see a reduction in the price of hydrogen. And that takes us to around 32% reduction on average. So on average is from now to 2050 and every year. So in some years it's higher and in some years it's less. So at this point, hydrogen becomes competitive with natural gas if natural gas prices are high. I mean, you will expect to see more hydrogen projects coming up in the UK, and we checked some of them are coming online in 2030 if the natural gas prices stay high and the government delivers on the ETS and the hydrogen business model. Now, if we take into account the size of SLBs today and what a hydrogen developer can get from the bond market, we see a reduction in the price over time by 7.6%, but the price drops in 2025 because the size of the market in 2025 is very high, and it reduces with time because the KPIs will be met with time, and there are also penalties on these SLBs. So what we've shown here is the potential to reduce the levelized cost of hydrogen based on these interventions used singly. What we want is for the new price to come down to be competitive with natural gas in an average scenario. So the policy is you have the UK ETS and then you have the hydrogen business model. Because the free allowance in the ETS reduces in that time period, and that it is the end of the HBM and the beginning of another policy. There's the policy timelines.
And then for the SLB, you're saying it makes most sense right now, but then over time, as all the companies meet their targets, then it doesn't.
Then the bond reduces, yes. The penalties will be more as you meet your target. So it makes sense today to leverage the SLB market, but not in the future.
Just to understand then, so on the dedicated, you've already incorporated the hydrogen business model continuation with the analysis as well as ETS.
Yes, so this will be under the policy, yes. So the dedicated is with no policy.
But hydrogen business model, the R1 is super expensive.
To deliver is super expensive. So what we've done is to create a scenario where the revenues from the ETS will fund the hydrogen business model.
So what price would be ETS?
So we'll use the ETS, the current ETS price today, and that will fund it. That will fund it entirely because the price is increasing with time. No, so it's only a proportion. I think we saw that 40-something% of the ETS can fund hydrogen. So not all the ETS. I'm not that fast. That's good. So we use the we use we consider three types of electrolyzers and models for each of them and took an average. I think the electrolyzer utilization was about 49% or so. And the load factors was about 40% load factor for wind. So we went with very average. We're not too optimistic, but also not too pessimistic.
How does that tie in with the, how does that tie in with the curtailment, which is much further than points?
That's the next set of results, yes. So if you apply these interventions singly, they all have some potential to reduce costs, but we're in a market where it's possible to blend the interventions. So what I've shown next is blending interventions. So we've seen the first four applied singly. What we'll be looking at is this two. So one is if we can utilize electrolyzer waste heat for district heating and also benefit from the current policy environment, then we have about 48% reduction in cost compared to the dedicated, and that's on average. So that's the average over the years. It changes from year to year. And if you exploit the SLB market as well, we have a further reduction. At some point, it becomes negative just because of the size of the SLB market today. I would say this is probably not possible. Well, we just had to go with the values we have. I think the market signal will push the SLB penalties up and will take us back to the positive end. But it just shows that with what we have today, by 2025, if it continues, that's the potential for cost reduction. Very unrealistic to be negative, but the blended interventions has potential to reduce the levelized cost of hydrogen. So we factor that into the prediction of hydrogen demand. So we looked at a case where sectors reduce their demand or increase their demand. There's a reduction in products that they offer. So we factor that into predicting the demand for hydrogen and compared it with base analysis as well as with the CCC analysis for industry to come up with an average. So it's based on that average that we're doing this analysis.
So what do you see as like the biggest by sector by 2050 sector?
Ammonia.
Okay.
Methanol. Kerosene. So we see increases that we use for aviation, refining. The UK don't have that much left on refining. Iron and steel was a big player until Africa. So that would draw the demand, and a lot of hydrogen for heating as well. With the energy intensive at temperature.
Yeah.
So these two analyses were based on dedicated offshore wind, no potential for curtailment was included. And if you remember the graph where I showed the potential for curtailment, it doesn't meet all the demand for hydrogen, but it contributes to hydrogen production. I think it's just in 2025 and 2050 that hydrogen from curtailed offshore wind meets 100% of the demand. And we go to curtailed offshore wind. So this is a mix. So this is a mix of dedicated and curtailed offshore wind. Based on that balance, you see that the levelized cost of hydrogen from curtailed offshore wind without any policy support at all is higher than dedicated offshore wind. I mean, if it's possible to use all the curtailed offshore wind for hydrogen or scenario, but I don't think it's possible. Well, again, we see this reduction in the levelized cost of hydrogen as a result of this intervention. So what you do with waste heat from the electrolyzer, existing policies, using the SLB and blending the interventions. And of course, we get to this point of negative hydrogen cost, which isn't feasible, but it just shows the potential of interventions to increase the economic viability of green hydrogen for use in industrial decarbonization. Now, in some instances, it's interesting to see that, when you blend policies, especially using just waste heat and waste heat utilization's existing policies and adding the SLBs in future years, the prices are very close because the SLB funding side or the private finance of SLB is in the future as companies meet their KPIs.
Just a quick question. It's not just about this one, but it's about the previous one as well. Clearly this is super complex topic. But in terms of thinking about the logistics costs to go from the curtailed offshore wind or from the offshore wind wherever to the customer for ammonia, there's not much ammonia production in the UK as far as I'm aware. But in terms of other areas, clearly that's not going to, the production profile is not going to match the offtake profile all the time. There's going to need to be logistics, maybe pipelines, maybe storages and stuff. Have you been able to incorporate that into your analysis?
No, we've not incorporated details about the logistics, especially when hydrogen is going to be used for other stuff. But we have a project starting up to look at power to X and the techno-economics of power to X. So we've done the power to hydrogen, or when hydrogen, if you want to use hydrogen for ammonia or methanol, the question of whether you situate the electrolyzers next to the offshore wind facility or onshore and just get electricity from offshore, the impact on the cost of the X is the next thing we'll explore and see how we can reduce that. We just feel as long as the price of hydrogen can come down, then the X will be something worthwhile to explore. Because when we look at ammonia, green ammonia, one of the key drivers, or even green ethylene, one of the key drivers to their own techno-economic assessment was the levelized cost of hydrogen. One key take-home message is blending interventions can increase the commercial readiness level. So with hydrogen, the technology readiness level is between 6 and 9. We've demonstrated it at scale, storage, combustion, using it as field. But the CRL is still one because it's not cost competitive. And one way to make it cost competitive is to blend interventions from policy instead of depending on the government, policy of the private sector, and what we can do within the perimeter of the systems or the technologies. And with that, it's possible to promote cost competitiveness. So this is just dedicated hydrogen from dedicated offshore wind, blending the three interventions and showing cost parity with natural gas. And same for curtailed offshore wind mix with blending all the interventions and showing the cost parity with natural gas, just to send a signal on how we can increase the commercial readiness level of green hydrogen for use in industrial decarbonization. And to summarize, what I can say is to make green hydrogen more competitive, we want to leverage technological breakthroughs, what we do with the electrolyzers, but system breakthroughs, so what you do with waste heat produced or the oxygen produced. We didn't do any case study on the oxygen yet. That's the next step to show how we can reduce the levelized cost of hydrogen, but ultimately reduce dependence on external interventions. That's the key. If we could get to a 50% cost reduction from these internal interventions, that's a good market signal for green hydrogen. And what we can see, a comprehensive approach to make it more competitive is to explore both internal and external interventions. And this is what we do for all the technologies we consider. So for CCUS, for direct air capture, we try and look at what kind of internal intervention can get economic value and reduce the cost, and what's the role of external interventions and how can we blend both interventions to achieve those economic endpoints. Now, This leads to the fact that if we have very good interventions, we can actually shorten the timeline to the market's saturation of these sustainable interventions. And I know the economic is not the only challenge, the affordability of these sustainable solutions is not the only challenge, but we want them to get to the market very quickly if we are to meet our climate ambitions, our net zero ambitions, and blending interventions may be the way to go. So I've come to the end of my presentation, and I'm happy to take any questions.
The industrial demand will require a consistent, reliable supply of hydrogen to prevent downtime. Have you considered the storage capacity required to provide the reliable supply when coupled with curtailed wind?
So we looked at the demand for hydrogen from industry, not just the annual demand, but the demand per time period throughout the year. And for most of the sectors that are driving the demand is constant. So we factored that into the price of hydrogen and into the energy balance of the model to see if it's possible. Where it's not possible, that's where we have dedicated offshore wind. We can extract from the model the size of storage required to meet the demand for hydrogen.
Kind of like government policy, what are some policies that you'd want the government to introduce to help reduce the?
I always like the mixture of carrot and sticks. Carrot and sticks. So you want to incentivize, but you also want to penalize. What we've seen is that grants are not very effective. I think, in my opinion, I may be wrong, but within the industrial sector, grants don't do a lot. So you either want to give dollar per ton of products as an incentive, or you want to penalize dollar per ton of CO2. If you want to bring the price of the conventional fuel based on fossil high, but you also want to reduce the price of the sustainable fuel. Now, how you incentivize depends on what the learning is from the technology. So for instance, the more you manufacture electrolyzers, the more their cost is, and bigger electrolyzers benefit from economies of scale. So the initial incentive is just to get us on that cost curve. It's just to get us on that reduction, and then you reduce it with time. Most times incentives are not set from the bottom up what's affordable, but it's set from the top down what governments can afford. What governments can afford versus what will affect the technology. That's what I've seen. So a government can set an incentive of $50 per ton of hydrogen, but that's dependent on what they can afford. Our job is to see what that $50 per ton can do as an incentive together with existing taxes, how much demand for hydrogen can that generate, and is the demand sufficient to get us on the cost reduction trajectory for hydrogen?
Thanks. Super interesting. In terms of what customers as well as governments can afford, this goes to the heart of the matter, really, doesn't it? And in terms of the incentives, efficiency in terms of driving efficient outcomes are very important. Have you looked at, to what degree the benefits of the vector specific, in this case, green hydrogen incentives versus, say, GHG reduction specific incentives, and given the uncertainty and the sort of multifaceted technological developments around the world, from my point of view, it would seem to be better to incentivize reductions in emissions rather than saying we want to go green hydrogen.
Yeah.
What have you looked at that?
So we've looked at having an intervention related to greenhouse gas reduction versus having an intervention related to specific vectors. An intervention related to reducing greenhouse gas emission is more effective, but what would you base it on? So it will be it could be a penalty on the dollar per ton of CO2, or it could be an incentive on a dollar per ton of CO2 reduced. But throughout the world, I've not seen an incentive on the dollar per ton of CO2 reduced.
Yeah, right.
The IRA is a tax break based on, so it's direct air capture, it's per dollar per ton of CO2 stored or utilized. And that one is, we assess the impact of the IRA for 45Q for direct air capture compared to the UK ETS, for instance. And that's effective in making direct air capture cost competitive. But it's difficult to measure how much CO2 is stored, so you kind of have to trust the data I have. Whereas it's probably easier to trust the data that says I have X ton of hydrogen in my system. But what we've seen is, because we looked at this policy singly and tried to combine different policy interventions, we're better off combining both an intervention on carbon and an intervention on the alternative. But they send different market signals.
So do you think, is there any interventions need to be prioritized?
Oh, that's a good question. I think as long as you have a carrot and a stick. So the EU allows for hypothetication. When we're doing analysis on the EU ETS, or so Germany has a carbon contract for difference, we see how revenues from the EU ETS can fund incentives, and that's a good evidence base for them. So to prioritize carrot and sticks. But UK Treasury doesn't allow hypothetication, so it's good to have a mix of the two. Now, it's also good to phase it. So it's possible to incentivize, because now you have early adopters, right, who will install hydrogen without any form of push or pull from government. So you want to incentivize them so that you can get that market demand, that market saturation required to reduce the price of hydrogen. And the laggards in the future, you just tax. And they would tax at a lower level because they would have benefited from the ripple effects of hydrogen price reduction because of the early adopters. So we've explored that's how you phase the policies over time, and you're saying that the optimal way is to maybe incentivize earlier on and tax the laggards, and you still recover money that was used to incentivize.
Two questions on the same person. The first one, I think it came through when you were going through the last couple of slides with results. He asked, does the base case assume technological improvements in efficiency? So I think it's when we're going through the study.
So the price for levelized cost of hydrogen from dedicated offshore wind accounts for technological improvement, the efficiency of electrolyzers, and that's what reduces the price over time. It also accounts for economies of scale based on the demand for green hydrogen.
And here's another question. He said, so if I've understood correctly, the mix of policy, waste utilization, and SLBs can bring green hydrogen into the upper range of expected natural gas. And if you can utilize curtailed wind, it drives it down significantly towards.
I can say that with 65% confidence. Based on our results from the worst case and the best case, 65%. That's probably not so good for policymakers.
So we heard a lot from the government over the past week about CCUS and the role that they see for CCUS in terms of sort of trying to decarbonise industry. I wonder if you could give an idea of the sort of costs of kind of converting industry to green hydrogen from where they are today, as opposed to continuing through fossil fuels, but with a kind of CCS, you know, on the plant.
So that assumes that you could do, so for the same plans, it assumes that you could do either, but it's not. So some plants will need green hydrogen. but some plants will still need CCUS. So if you take cement manufacturing, you still need to capture CO2. You cannot use hydrogen in that sense. Iron and steel, that's one where you could use green hydrogen green hydrogen for direct iron reduction, or you could leave the blast furnace as it is and integrate CCUS. Now, for that case where you could have both options delivering the same ambition, green hydrogen is more expensive. The calculation we did for all iron and steel plants globally, it was about 5 times more expensive. And 5 times, we're not talking about 20 to 100, we're talking about billions of dollars. But the price of green hydrogen will come down in the future more than CCUS, and at some point, but it still was never more cost effective compared to just using CCUS with a blast furnace to capture the CO2. So the economic driver is towards CCUS for very energy intensive sectors, except we can find a way to reduce the amount of green hydrogen. And with green hydrogen, I know I'm only concerned about the economic challenge, but there's also the renewable availability. And for this particular case study, it was for a particular country, you need to double the grid capacity to use green hydrogen for their iron and steel sectors, because they export a lot of iron and steel to other countries.
I was wondering whether you built in the assumption that the government is successful in its, plans for 2030 decarbonisation
of the grid.
Yeah.
So that's what
that makes it
dedicated. So we use dedicated offshore wind. We're not sure. The government is serious about those plans. Yeah. Well, using dedicated offshore wind gives that low carbon.
So like additional.
Yeah.
Yeah. Okay.
Thank you very much for the great presentation. My question is from the perspectives of the industrial operators. How do you envisage the requirements of change in the infrastructure when of taking this great amount of hydrogen? For example, how many or how much change do they need to implement in their boilers, for example, to be able to, offtake this amount of hydrogen?
That's a good question. It depends on the sectors, right? So some sectors already use hydrogen. In fact, some of them already combust fuel gas, which is a waste gas. That is a mixture of hydrogen, natural gas. They mix different waste gases and combust it to generate heat. So those ones already have some form of infrastructure to handle hydrogen, especially within their boundaries. And those will be the early adopters of hydrogen. And in most of the cases, those will probably be the only users of hydrogen. So the cost to them to change the combustion system in the boilers or to change the structure or the pipes is negligible, not negligible, is little compared to sectors that don't use hydrogen at all.
Thank you.
Asked, are there projects that have successfully demonstrated waste heat harvesting in electrolysis?
There are projects in the that have done that harvesting, and we're currently doing some analysis for SSE on that for the UK. I'm not that technical to harvest the waste, but is the economic potential that drives the harvesting. But there are projects in Denmark where they've successfully demonstrated waste. So our analysis is built on a demonstrated project. It has to be demonstrated before we make viability. It cannot be demonstrated. We wait until that concept gets the entire LOB before we start looking at how to make it economically viable.
Thank you for your presentation. Really interesting. I'm from a completely different field, so maybe it doesn't make sense what I'm going to ask, but I would expect that there will be also policies to try to avoid the curtailment of wind. So would that not be like underproducing or affect what you're modeling there?
Thank you. That's a very good question. There will be policies to try to balance the grid and what the electricity markets can do. There will probably be reforms of the electricity market to prevent curtailing wind because of how much it's costing everyone. But there are also there are also discussions on what to do to not curtail wind. So if hydrogen becomes a load, then there will be no concept of curtailed wind anymore. And I agree. So we'll go back to dedicated offshore wind. But that's why I've presented the two results separately. So that means we're left with all dedicated offshore wind, and that's the potential to reduce cost. And if there is, and I think the frequency of curtailment will reduce with time as well as we boost the grid's flexibility and things like that. But the results will now be between the dedicated and the curtailed mix. So the curtailed mix that I've shown would be an ideal scenario.
In terms of like assessing demand, I was wondering, do you expect the threat of like some of the UK industry moving overseas, therefore affecting, the hydrogen demand projections?
It will. So there are two things that are happening. Regional industries may move overseas, but we've seen an influx. We'll see an influx of new industries, especially related to e-fuels and sustainable aviation fuels. And those ones, their demand for hydrogen is going to hit the roof. So we've tried to understand the probability of these foundation industries leaving on the impact of the hydrogen demand to come up with this scenario. But yeah. I'm hoping they don't all leave.
Likewise.
But we'll see the birth of new industries. I think greener industries as well.
Just a point of detail on your charts. Were you looking at prices on a wholesale basis or on a delivered basis?
So for electricity,
for hydrogen.
Hydrogen, it's a retail delivered basis for industry. The wholesale price was less. 30% less. There's a hand online. I don't know how to. Do you want to ask your question, Jack, or do you want to type it? Yes. Yeah. I can't control it.
There's another question here that says, are there projects that have successfully demonstrated waste?
Yeah, I've answered that one. Sorry.
Next question. What do you think the profit margins of hydrogen supplies of hydrogen? Those analysis of hydrogen today is based on the
Yes. So we do some stakeholder engagements where we're building the model, and most people say 20 to 30% is good. But the levelized cost of hydrogen we factor in here is delivery to industry. So the wholesale will be lower. But what we calculated as a wholesale was 30% less than that. I mean, there's also the project cost, because I'm saying levelized cost is just an indication. But there's a total cost as well to consider. So we walk from the levelized cost of dedicated hydrogen to the total cost and then back to the levelized cost. So we'll factor in all the peripherals in that cost chain.
They said industrials looking to decarbonise with hydrogen that's reliable and affordable. Have you looked at the practical difficulties in transporting and storing hydrogen as opposed to producing hydrogen on?
So my scope is making hydrogen more affordable, reliable. There's a fantastic group at Imperial that does that. But I just look at how to make it affordable. So the practical difficulties in transporting and storing, it's not within my scope. I can talk about it, but I'm not the expert. That's it. Okay then. Thank you all for sharing your lunchtime with me again, and have a lovely rest of the day.
No, I'm on,